So the first project to showcase here is, as far as I know, is the largest rural water project in the world. It is called the Minnewaconing Rural Water Supply System. It is located in South Dakota. In the upper left of this figure here, you'll see an outline of the state of South Dakota. And this project encompasses approximately 1/4 of that entire state. What I have highlighted in red is the portion that my firm worked on. That's something called the core pipeline. It starts in Pierre, South Dakota, there where we built the treatment plant, and we convey water to this entire service area, 10 counties, through that core pipeline. A couple quick statistics about this project. But these are specific to the Ogallala Sioux Reservation, which was in the lower left-hand corner of that previous slide. It took us 125 miles of that core transmission to get down to the lower left reservation there. It started out at 24-inch and it ended at 12-inch, but it was almost entirely 24-inch. Then we had 220 miles of distribution main, 12-inch to 3-inch. And then another 200 miles of 2-inch and smaller PVC pipes. You can see there was a lot of piping involved in that project. 95% actually, as I tallied it up later. So there's, these stats I'm giving you are only for us to do the core main down to our local tribal project we sponsored. There's a few here that got served. Photo on the right, I particularly liked it. The ponies got loose and got on our project site there, but what you do see is the PVC pipe going up the hill. I want to point out that that orange blob is actually a polyurethane insulated concrete vault, and I'm going to make particular mention of that because alternative idea is using the old standard concrete manhole. Sure. Second project, not going to let the name out on this one, even though it's probably well known in the state of Arizona at this point, but it's a Northeast Arizona rural water supply project. It's approximately 50 miles long. It's in the design phase now, and I can't honestly say that. It's in the feasibility phase right now. But there's a pretty telling photo of what the design challenges are for this project. Where South Dakota's plains, this is desert mountains. Total length is 50 miles. It's going to start out as a 30-mile, going to start out at 30-inch and reduce down to 12-inch. Design flow is just under 10,000 GPM. Challenging terrain, I think the photo explains that. Yes, we are putting this pipeline through that terrain. We ended up being 90% PVC material for our piping, and then the rest was 10% have to be metallic. And then we had 160 bolts, and on this one, with the help of the fellows at Diamond Plastics, we came up with an alternative method using PVC pipe in lieu of concrete bolts for these rural water projects where traffic load bearing was not required. So some commonality between these two reference projects. Not all rural water projects will experience these common points that I'm going to exemplify. It's the soils. It's the fine-grained natures of these soils. And even though you saw that Arizona photo, we don't target rocky areas for putting a pipeline through. We look for the loose soil to trench these in. But you can see in UCS class, clay and sand, that's very common. Not the best, honestly, when you're doing your embedment and your percent deflection calculations for flexible pipes. Soil resistivity is a huge deal. Very typical that on both those projects, doesn't matter South Dakota, Arizona, we got many in Montana, we are consistently below 1,000 centimeters for resistivity. That probably means very little to this group. You're probably going to frown at me for So, corrosive soil design. I can't imagine any of you want to hear this at all, and I'm sharing it with you because I don't want to speak about it either. I want you to know what the metallic pipe industry faces, and this is reason number one for me to go to a PVC pipe in corrosive soils. So, not to teach anybody, I just want you to know what is involved here. Up at the top, 3 different standards. Yeah, just pick one. In the middle, because these are reclamation jobs typically that my firm is doing, we're forced to use the reclamation design guides. So I listed a TM. It's a miserable document. It says soil resistivity less than 2,000 centimeters. Your steel and your duct will require these 3 following, not one individually, all of them. Down at the bottom, PVC is just not listed. Everybody appreciates it as not being corrosive. So a little bit more about those 3 elements that are required. I mean, bonded dielectric coatings, I know what they are. I'm not ashamed of that. I'm kind of proud. But it's knowledge that what frustrates me is I'm not licensed to actually design those. I am a hydraulic engineer. I do pipe day in and day out. Every project I do, I have to get a specialist corrosion engineer to help me with that. Very frustrating. Tight bonded coatings, though, I know what they are. I just can't do them technically. Corrosion monitoring test stations. A little figure on the right. It's O&M. It's time. Somebody has to go out and check those stations. That's part of our O&M manual. We give the client when we're done. Cathodic protection. I think everybody's probably familiar with that. Galvanic anodes, sacrificial metals, impressed DC currents. There's a lot of there's a whole industry in itself. We'll just leave it at that. Thank you for listening to corrosion. PVC pipe. Okay, now on to the stuff I can't speak to with some amount of excitement. Hydraulic and transient performance specific on this slide is the hydraulic capacity. Down at the bottom there are 2 plots. I created them. I included them in one of the submissions to the Bureau of Reclamation as defending or supporting why we choose wet pipe when we do. When it comes to hydraulic capacity, just jump right down to the bottom plot. Mind you, this is ID, even though on the bottom it seems like those are nominal numbers. The data used here is actual ID. 150 Hazen Williams for PVC, 130 for cement line ductile. And you can see that if we held the velocity constant, and that velocity is way too high, I never designed that, but it actually gets a little bit of a curve in the graph there. You see that PVC is the more hydraulically efficient on head loss, holding velocity firm. On the right, holding the flow rate fixed. So then what changes? Well, because each pipe has a slightly different ID, well then the velocity changes. Couple that with its different friction factors, you get a change in the curve, but again, what do you see? You see ductile iron and PVC iron getting close together. The anomaly on the left with the 12-inch pipe, it's the dimensional standards for steel, for AWWA steel. They have a break point at 12 inches. Anything after that, the OD is actually nominal. I really took off there. So quick jumping over to one variable in transient performance. And when I say transient performance, I mean surface. Everybody's probably familiar with water hammer, and that's exactly what we're talking about. What is wave speed? Wave speed is the defining pressure wave for propagation in a pipe. Each pipe material has a different wave speed. Why? Because of those 4 bolded items. The ID, the dimensional characteristics, wall thickness also. Then the elastic modulus and elasticity also. And then your restraint method, talking about joint This all boils down to one simple takeaway as I look at my time. The lower the wave speed, the better the performance of the system. And PVC, by far, has the lowest wave speed of ductile iron or steel. You can see it changes just a little bit with your DR. That's reinforced on the right. Sorry for the metric units on my plot there. But again, PVC down in the very lower left corner. Again, reinforced the point. Slower the wave speed, better performance for surge radiation. There's a flip side to that, and that is the more friction you have after a surge event has already occurred, the better the mitigating effect. So it's a double-edged sword. Hydraulic efficiency is definitely boosted by PVC's high Hazy-Williams coefficient, but mitigating or controlling the surges that occur on a PVC project can be a little bit problematic, and I won't say that it'll be the worst either. It's still a good material to work with for surge events. This is just one variable that is going against PVC, but it's a good variable to have every other time. So I won't read through those anymore. It should spell it out pretty good. And I don't want to go into a lot of time on this either, but I did include a surge plot. David Munn will be presenting to you on Wednesday at this conference. His topic is transient or surge analysis in some part. So I'll leave that to him. Again, I could personally get lost in the clouds on this one, and I would love to drag you all along with me while I did it. So, flexible pipe deflection analysis. I think everybody's probably aware here, who's in the pipe industry, about the AWWA method. Well, AWWA actually has this method for steel, ductile, and PVC. Every one of them is based off a modified Iowa formula. I've got intimate with all of them. And then these Bureau projects that are Bureau, our rural water projects that the Bureau has their design guidelines enforced on. I had to get familiar with their manual M25, which is the Iowa formula, not the modified, and it's a variant of that. Again, the one common point between the Bureau and the AWWA formulas is that the percent deflections that are acceptable, they're all held the same. What the Bureau does with their formula is they add a time lag factor and another design factor. It's tough. The result of that is, if you were to compare, this is the PVC pipe table comparison, but I got the nominal diameter on the left, DR there, next column, and then the AWWA method, delta Y, so it's the change in vertical direction. In percent, you can see that the AWWA method historically, if you were using that, it gives you some, I won't call them conservative, I'll just call it the numbers. And then the BOR method gives you much higher predicted percentages to a factor of 2.4 to 2.9 times as much as the AWWA standard. So what am I to do with this? The Bureau tells me to use their standard. I use it. What the results in is, if I really want to use PVC pipe in this particular location, the diameter is too big, there's not enough stiffness, the deflection exceeds 7.5%. It's not a catch-22, there's a way to deal with it, but you all should know if you're not aware of the Bureau standards. So with just 1 minute left, I just wanted to wrap up with some simple costs. I think everybody in here knows where you stand in relation to the competition with ductile or steel, if you even see them as your competition. I just went back to some old costing estimates. These are both within the last 2 years. Rural water projects, unnamed though. I'm not going to give you all of it. But this is what we came up with. This is our own independent assessment of cost. So when the pressure class isn't hampering us, when corrosive soils isn't hampering us, other design restraints, we leave it to cost. That's one of table speaks for itself. And then the last one, I did mention at the very beginning that we were trying something new with our vaults. They house our valves, our ARVs on these long projects. Anything metallic or a device that needs to be accessed, we'll throw it in a vault. Historically, we done with concrete. We heard about the new large diameter pipes coming out. Well, 30 was the biggest we needed for our most recent project, but we thought, well, how can we put it to use? That's the idea. A standard detail using PVC vault. The big deal here is it's about $2,000 worth of savings per vault. If you remember my very first slide, I showed you 1,000 vaults on that 125-mile section of pipe. I don't need to do the math for you. The other good thing about it is that from my standpoint, when I see all these concrete manholes being shipped out to these job sites, very remote job sites, and then they don't quite fit, right? A PVC pipe, 60-inch diameter, cut it to length, stand it on edge, everything's good. And then just a quick note at the bottom, we actually did get some help from Univel and from Diamond Plastics as we calculated whether or not this was going to work, and we did prove it would. My last slide. So thank you again for the opportunity. Hopefully this was interesting or maybe a little insightful. And if you have any questions, please.
Okay. Yes, Vesa?
Can I ask one question? How did you deal with air entrapment throughout that 125-mile line?
Air entrapment. Okay. With ARVs, air release valves,
Yeah,
vacuum valves. Yes. That's how we dealt with it. That's where those 1,000 concrete vaults come from.
Okay.
Every time we put an ARV in, we put it in a vault.
So you had 1,000 of them in the 125 miles?
Approximately. Yes. Yeah.
Very good. That's very impressive. Thank you.
Excellent. Okay, just a housekeeping note. This evening, there is the welcome networking reception taking place off-site. The shuttle will be leaving at 4:15 in front here. Now, also remember, there's a dinner this year that comes with the networking welcoming reception, and S&B Technical has sponsored the event, so we look forward to seeing you all there. And